Okay, welcome to this new video of Math-S401 dynamic optimization. The problem that we're going to look at today is called the longest common substring. So to explain the problem, let's assume that you have two words, right? And the word is just a combination of letters, so they don't have to be English words or have anything meaningful to say. So for example, word 1 is A, B, C, D, A, F, and then you have a second combination of letters A, C, B, C, F. Okay, and the question is the following. What is the longest common substring of the first word and the second word? Okay, so for example, I have a common A here. I also have a B, and for example, I have an F. Okay, so ABF is a common substring. Okay, so the letters have to, the order is important, right? A has to come before B and has to come before F, but there can be gaps in between. Okay, so here the C is in between, but I don't care as long as A is before B is before F. Okay, that's a common substring, and I would like to find the longest one. So here I have ABF, but there are longer ones that I can find. So what you can do is, for example, you can, for word 1, you can consider the set of all possible substrings. Okay, the same for word 2, and then look for which ones are the same, and then try to find the longest one. And okay, this is, I hope you can see that this is a very inefficient way to find the longest common substring. So here we're going to use dynamic programming and try to find a more efficient way to do it. Okay. So in order to do this, let's, instead of using these letters, let me say that word 1 is just a combination of letters, and let me call the first letter x1, the second one x2, and so on. Okay, and assume that I have in total big N letters in this word. So x1 is here A, x2 is here B, and so on. Okay, and for word 2, so this is word 1, word 2, I have the same thing, but y1, y2, and so on until ym. So here the length of the word is big N. Okay, so y1 is A, y2 is C, and so on. Okay, and as usual, I have a function v that takes in these two words, x1 until xn, and y1 until ym, and gives me the length of the longest common substring. And as usual in dynamic programming, I would like to write this function v as a problem that can be expressed in terms of maybe also the function v, but then in terms hopefully of shorter substrings, right? Like a subset of the original problem. And then I can recursively solve it by first solving the smaller subproblems and then finally solving the bigger one, leveraging the fact that I already had a solution on the smaller problems. Okay. So in this case, if you think about it, there are a couple of cases that you can consider. And here the idea is to recurse on the last letters. Okay. So if you have a common substring between x1 until xn and y1 until ym, then it's possible that these two last letters are the same. And if they're the same, they can be part of the longest common substring, right? So for example, here f was the same, so you can think maybe they're part of the longest common substring. Okay, so if xn is equal to ym, right, so the last two letters of these words are the same, and if they're part of the longest common substring, let me abbreviate it as this, then what's the value of the longest common substring? Well, first of all, these are part of the longest common substring, so I have 1, the length is at least 1, plus maybe if I remove these two, right, because they're part of the common substring, what I have then is the word x1 until xn minus 1 and y1 until ym minus 1. Okay, so this is now my smaller problem. I take the longest common substring these two words and I add 1 because the last letters are also the same. Okay. Else, if it would happen that these two are not the same, or they're not part of the longest common substring, well then I know that either xn is not part of it, or ym is not part of it. Okay. Well, if xn is not part of it, well then the longest common substring, I can remove xn and write this simply as x1 until xn minus 1 and y1 until ym. Okay, because the last letter is not part of the longest common substring, I can simply remove of it and this value will be equal to this value. In the third case, it's possible that ym is not part of it, and then I can write it as being equal to this, the word x1 until xn and y1 until ym minus 1. Okay, so either I can remove this letter or I can remove this letter, and the longest common substring doesn't change. Okay, so basically there are three cases. Either the last letter is the same and they're part of the longest common substring, or I know that xn is not part of the longest common substring, or I will have the case that ym is not part of the longest common substring. Okay, and of course, because here I take the longest one, basically I have to take the maximum of these three cases. Okay, so my Bellman equation will be the following: vx1 until xn, y1 until ym. Well, this is going to be equal to the maximum of number of cases. Either xn is not part of it, and I have this, or ym is not part of it, and I have this. Or it's possible that the last two letters are the same, and then I also have to consider 1 plus v x1 xn minus 1 and yn until ym minus 1, and then plus 1 because the last letters are the same. Okay, so this is my Bellman equation. Either we have this case, or if the last letters are the same, I also have to consider this case as possible being bigger than these two. Okay, so this is my Bellman equation. And of course, I also have to consider base cases, right? What's the smallest problem that I can tackle? Well, so either this, if I go to the right hand side, either this one will become shorter or this one will become shorter, or they're going to be both shorter. Okay, so after n iterations or m iterations, right, one of the two substrings will be equal to 0 length, right? There will be no letter in there anymore. So if I have a substring that's empty, let me write it like this, and some word on the right hand side, let me write the word like this, then of course the longest common substring has to be equal to 0, right? There's nothing here, so I cannot find any common substring that's of any length. And the same way here, if I have a word here, x1 to xn, and I have the empty string on for the second word, then again this has to be equal to 0. Okay, so these are my base cases. Okay, so let's see how this works if we make a table, right? So we have two words, so what we can do is we can make a table where every row is a letter, let's say of word 2, and every column is a letter, let's say of word 1, and then we build up this matrix row by row or column by column in this way. Okay, so we have a table. Let me put A, B, C, D, A, and F. So these are the columns. And then in the rows, I have the letters of the second word, A, C, B, C, F. And basically, I also have the empty string here, right? So these are the base cases. So I already know that for the empty string, these all will be equal to 0. C0, D0, this one 0, this one 0, and here I have zeros. So these ones are a bit close together, but I'll hope I'll manage. Okay, so basically what I need to do is, for example, let's take the substring which has the letter A, and here also the letter A. Okay, then there are three possible cases. Either these two are the same, okay, and I can consider the value of 1 plus V of whether I cut the last letter of both substrings. So basically this is 1 plus the value I get when I move one to the left and one up, right? Because this means I go to the substring without the last letter here and without the last letter here. So this would be 1. Or I just cut the last letter of the second word, so I move one to the left, which is 0. Or I move the last letter of the second word and I move one up. Okay, so I have to consider this value, 1 to the left, or this value 1 up, or 1 plus the one to the left and up, in case the two last letters are the same. Okay, so here these two letters are the same, so I have 0 plus 1, or 0 or 0, so the maximum is equal to 1. So I have this value. For here, A is different from B, so I either take the maximum of 1 to the left, which is 1, or 1 up, which is 0. So here I have 1. Okay, A is different from C, so I have the maximum of 1 or 0, which is 1. A is different from D, so it's maximum of 1, 0, and 1 or 0, which is 1. A is equal to A, so here I take the maximum of 1, of 0, or 1 plus 1 left and 1 up, which is 0. So it's a maximum of 1, 1, or 0, which is 1. Okay, and here A and F are different, so I simply take 1. Okay, so this is my first row. And you can see you can easily fill in this table very quickly. So C is different from A, so it's a maximum of 0 or 1, which is 1. C is different from B, so I have 1 or 1, which is 1. C is equal to C. Okay, so I have the maximum of 1, 1, or 1 plus 1, which is 2. So here I have 2. C is different from D, so 2 or 1, which is 2. C is different from A, so I have 2. C is different from F, so I have maximum of 2 or 1, which is 2. For B, B is different from A, so here I have the maximum of 1. B is equal to B, so here the maximum of 1, 1, or 1 plus 1, which is 2. So I will have a 2. B is different from C, so the maximum of 2 or 2, which is 2. B is different from D, so I have 2. B is different from A, so here also 2, and here I will also have 2. Okay, C is different from A, so the maximum here is 1. C is different from B, so the maximum here is 2. C is equal to C, so I have the maximum of 2, 2, or 2 plus 1, so here I have 3. C is different from D, so here I have 3. Different from A, so again 3. C is different from F, so I have 3. And then for the last one, F is different from A, so I have 1. F is different from B, so I have 2. F is different from C, so the maximum of 2 and 3 is 3. F is different from D, I have 3. Different from A, so I have 3. And here F is equal to F, so I take the maximum of 3, 3, and 3 plus 1, so this is here 4. Okay, and you can backtrack to find the solution, right? So here I increased 1, so the F's will be the same. So if I remove F from both, I have this subtable. And here I see that the jump will be at C. Okay, and then if I look here, the B's will be equal. And if I look here, then the A's will be equal. Okay. Yes, here, this one. So I have A is common, B is common, the C will be common, and the F will be common. So I have the longest common substring is of length 4. Okay. So let's look at how many computations we have to make. right, we have n columns, right? That's the length of word 1. We have m rows, so that's the length of word 2. And for every cell, basically, we have to take the maximum of 3 things, right? So 3 is a constant number. We have to make 3 computations and take the maximum. So, right, this is constant time. It doesn't increase if I would make the words longer or bigger. Okay, so this is just a constant factor. So this is of the order n times m. Okay, so this is the complexity of this thing here. So let's try to program this. Okay, so here again we're at Julia. So I already written down my word A, B, C, D, A, F, and the second word A, C, B, C, F. Okay, so I would like to write a function, the longest common substring, and I will give it 2 words, word 1 and word 2, and then I hope it will give me the length of the longest common substring and maybe also the common substring that has the largest length. Okay, so I'm going to call this function with word 1 and word 2 at the end. Okay, so first of all, let's first store the length of word 1, and m is going to be the length of word 2. Okay, and I'm going to look at substrings, so I'm going to give it the length of the first word and the second word, and then the value v will be a function of these 2 numbers. Okay, so v, I'm going to store it as usual in a dictionary, so it's going to take 2 numbers, the length, the length of the subword of word 1 and the length of the subword of word 2. So let me store this in a tuple of 2 integers. I'm going to return also a number, right, which is going to give me the length of this substring. And then let me also store the word, the longest common substring itself. So I'm going to give it the tuple, and I'm going to return a string. Okay, a string is something in Julia that's basically a combination of letters, like this here. This is a string, word 1 is a string, and word 2 is a string. Okay, so far so good. And then at the end I'm going to return v and LCS. Okay, it's awfully slow because I made an error somewhere. Yes, here, of course. So far, so these are not curly brackets, but just brackets. Okay, so this is Monday, so I'm the day is still early. Okay, so so far so good. So let's first look at the base cases. Okay, so for length of word I, for word 1, for 1 to n, v of I0, right? If the second word has length 0, then we're going to put it equal to 0, and LCS of v of I0, it's just going to be the empty string, which we can denote by this. And then vice versa, for j equal to 1 to m, v0j is going to be 0, and longest common substring between an empty word and the word of length j is going to be equal to the empty string. Okay. So these are the base cases, and now we have to the real work, right? So for the length of word 1, from 1 to n, for the length of word 2 from 1 to m. Let me close the loops first. Right, so there are three cases. If word 1 at this position is equal to word 2 at this position. Okay, so this is if the last letter is the same. And if it would happen that 1 plus v of I minus 1 j minus 1, right? So the last letter is the same. If these are part of the common substring, then this is going to be the value, right? If this is bigger than vi minus 1 j, I have to use square brackets here, sorry. And then within I have a tuple, right? And if it would happen that 1 plus v I minus 1 j minus 1 is bigger than v ij minus 1. Okay, so I have these three cases. If the last letter is the same and 1 plus this thing is bigger than if I would omit the last letter of the first word, and if 1 plus cutting the letters of the last words is bigger than cutting the last letter of the last word, well then I have that v of ij will be equal to 1 plus v I minus 1 j minus 1, and then the longest common substring of ij. So all these also have to be square brackets. Right? I will do this before I obtain an error in compiling this. So square bracket here and a square bracket here. Ah, come on. Okay. Then longest common substring. What's the value? Well, it's longest common substring of I minus 1 j minus 1, and then I have to add the last letter. And I can put two strings together or add a letter to a string by using the multiplication here. So I just add the last letter of word 1, but I could also have picked word 2, right? Because they're the same letter. Then else if, okay. So if this is not the case, right, but v I minus 1 j is bigger than v ij minus 1, well then v ij, I'm going to put it to v ij minus 1, and the longest common substring of ij is going to be longest common substring of ij minus 1. Okay. And then else vij is going to be equal to v I minus 1 j and the longest common substring of ij is going to be equal to longest common substring of I minus 1 j. So I have three cases, right? Either the last letter is the same and the longest common substring, if I put them equal, is bigger than if I would just drop one of the two last letters. Then I update it like this. Else, if omitting the last letter from the second word is better than omitting it from the first word, I have this. And then else I just omit the last letter of the first word. Okay. And let's see if this compiles. Probably not. Okay. So this should be two equal signs, right? Because it's a logical operator. Key 00 not found. Okay, here I have to go from 0 to n and here also from 0 to m, right, for the base cases. Forgot the 0 cell. Typo. Nope, this doesn't. LCS. Okay, I have something. So the longest common substring for 5 is 3. Right, let's see if this gives me something that I can work with. So let me put it in V and LCS. Let me save the results. So V of, so what's the length of my word here? 1, 2, 3, 4, 5, 6, and I have 1, 2, 3, 4, 5. Right, so this should be V 6, 5. So the longest common substring is of length 4, which is also what we found in the table. And what's this longest common substring? Well, it's A, B, C, F, which is also what we found in the table. Okay. Okay, so this is the matrix multiplication problem. So consider two matrices. So for example, here we have a matrix of size n times m, and then we have a matrix B of size, let's say, m times k. Okay, so this is an n times m matrix, and this is an m times k matrix. And you would like to multiply these two matrices together. Now, how many operations do you need to do in order to do this? Well, you know that you need to first multiply every element in a row by every element in a column. Okay, so in general you have m times you have m multiplications, and then you have to add them together, and you have to do this how many times? This m multiplications, well, you have to do it for every row and for every column. Okay, so in general you have m times n times k multiplications, or you can, maybe it's easier to write this as n times m times k. So you have the number of rows times the number of columns of the first matrix, which is equal to the number of rows of the second matrix, of course, and then the number of columns of the third matrix. Okay, so this is basically the number of operations to multiply a matrix of size n times m times a matrix of size m times k. Okay, so far so good. Now let's assume that we have 4 matrices, A1, A2, A3, A4, and you would like to multiply them all together. Okay, so we can do this because number of columns of matrix 1 is equal to the number of rows of matrix 2. Number of columns of matrix 2 is equal to the number of rows of matrix 3, and so on. Okay, so we can multiply them together, making the product A1 times A2 times A3 times A4. And the question is now how to do this in an efficient way, in the sense that you want to minimize the number of operations you need to do. And you know that, for example, what you could do is first multiply A1 and A2 together. Okay, then take this result and multiply this by the matrix A3, and then finally multiply the result of these multiplications by A4. Okay, so this is one way in which you can multiply these 4 matrices together. Of course, by associativity of the matrix multiplication, one thing that you can, for example, do is first multiply A1 and A2 together, then multiply A3 and A4 together, and then finally multiply the resulting 2 matrices together. Okay, and in general, because these are of different dimensions, and the number of operations that you have to do here will not be the same as the number of operations that you need to do here. Okay, so one multiplication might be more efficient than another one, and the question is now how to do this in the most efficient way. Okay, do you first compute this and then multiply the result by this and then the result by this, or do you, for example, first multiply these two together, then these two, and then multiply the result together? or do you take any other kind of combination? Okay, so for example, you could, first multiply A2 times A3, then the result times A1, and then the result times A4, right? This is another possible combination. Okay, so how many types of multiplications can you do? Well, it depends on how and which order you can put all these brackets. Okay, and in general, there will be a lot of ways in which you can put these brackets. Assume, for example, that you have 10 matrices that you have to multiply together. You can imagine that you have possible sequences of brackets that you can compute and in which order you can compute them. Okay, so here we're going to solve this problem for this particular example. So you have these 4 matrices, and we would like to know what's the most efficient way to multiply them together. Okay, so here our function v will be the number of operations in this sense, okay, of multiplying all these matrices together. And v, so this has to be a function of the state. Okay, so what we will do is we will consider subsequences of this sequence A1, A2, A3, A4. Okay, so subsequence could be A1, A2, or it could be A2, A3, right? Because we can consider different subsequences of multiplications. Okay, so for example, if you want to compute the product from matrix K until matrix L, okay, so this will be the number of operations to multiply matrix AK times matrix AK plus 1 until matrix AL. Okay, so this is what we're going to do. So if you put K equal to 1 and L equal to 4, then we know A1 times A2 times A3 times A4. Okay. Okay, and you would like to write this in terms of a subproblem, as usual. So here the subproblem is obvious, right? So if you have matrix AK plus 1 until AL, then basically what we have is that we can split this up in 2 sub brackets, right? So for example, from AK to AJ, and then from matrix AJ plus 1 until AL. And the question is, where will we put the split? Okay, so the split can be here at AK, could be at AK plus 1, could be at AK plus 2, and so on until AL minus 1. Okay, so these could be all the splits. So this is going to be an important question. Where are you going to put the split of the first sub brackets? Okay, and you can put them at different positions. So assume that you put them at position J. Okay, so then what's the total cost of multiplying this sequence of matrices together? Well, then you have AK times until AJ. Okay, and you multiply this by AJ until AL. Okay, so this is now the total cost. So this will be a matrix of size, let me take the rows of matrix K times the columns of matrix AJ. Okay, and then this will be a matrix of size rows of matrix AJ, and then the number of columns will be the columns of matrix L. And of course, the columns of matrix J will be equal to the rows of matrix J plus 1. This should be J plus 1. Sorry. Okay, so this is basically the subproblem that we have. So how much does it cost to multiply these 2 matrices together? Well, it's RK times columns of J times columns of L, right? This is this formula here. So if you put it at position J, then the cost of multiplying K and L together will be RK times CJ times CL. And then of course we first have to, in addition, we have to make this product, okay, which is VKJ, and then we have to make this product here, plus vj plus 1 L. Okay, so if you put the brackets at position j, then this will be our minimal cost. Of course, we don't know where to put the brackets, so because this is the minimum number of operations we need to do in order to multiply from AK to AL, we will put the brackets at the position which minimizes this cost. Okay, so this gives me the following Bellman equation, that the cost of multiplying from matrix K to matrix L is going to be the minimum. Okay, so the minimum of where we're going to put the brackets. So K is going to be less or equal to J is going to be strictly less than L. Okay, because we put J here, so it cannot be equal to L, because then we have to put the brackets before L of number of rows of matrix K times the number of columns of matrix J times the number of columns of matrix L plus the cost of matrix multiplying from K to J plus the cost of multiplying from J plus 1 to L. Okay, and I'm going to minimize over all possible J's. Okay, so I have to compute this for all possible J's and then take the minimum. And this is going to give me this number. Okay, so this is the Bellman equation for this problem. So let's try to make a table. All right, we're going to try to compute this. So what I'm going to put here is I'm going to put matrix 1, 2, 3, and 4, and here the same A1, A2, A3, A4. Now I can already, so what I forgot was to put the base case, right? So here we see that VKL is written as VKJ, where J is smaller than L, plus Vj plus 1L, where J is greater or equal to K, right? So it's basically written as a function of the subsequences. Okay, so what's the smallest subsequence? The smallest subsequence will be where there's only one matrix, right? So this is V, for example, KK, right? And this is only one matrix, so here the number of operations is going to be 0. You don't have to do anything to multiply a matrix by nothing. Okay, so that's what's stated there. So if you use the base cases, then these will be the ones on the diagonal. Also, all these numbers, A2 to A1, these are going to be impossible because you have to multiply forward, right? Multiplying A2 times A1 doesn't make sense because you want the product of A1 times A2, not the reverse. Okay, so these are going to be empty, and now we only have to fill in these values here. Okay, so let's first look at V12. Right, so this is the multiplication of matrix 1 times matrix 2. Here J doesn't exist, right, because there's nothing between these. So basically J is equal to 1 here. Okay. So you will have, let me write it down explicitly. So we have minimum of 1 smaller or equal to J smaller or equal to 2, and there's only 1 here, right? So here J has to be equal to 1. Okay, of V1J plus Vj plus 1, 2, plus the number of rows of matrix 1, which is 2, times the number of columns of matrix J, times the number of columns of matrix 2, which is 6. Okay, and as there's only one of them, J has to be equal to 1 for this minimum, right? So this is V1, 1 plus V2, 2 plus 2 times Cj is 3, 2 times 3 times 6, right? So this is equal to 0, this is equal to 0, 2 times 3 times 6 is 6 times 6. This is 36. Okay, and this is easy. This is simply multiplying matrix 1 and 2 together, right? You get 36. This is a bit more elaborate. So if you multiply matrix 2 and 3 together, you will have the same thing, right? So you have the number of rows of matrix 2, which is 3, the number of columns of matrix 2, which is 6, and the number of columns of matrix 3, which is 4. Okay, so this is 3 times 4, which is 12, times 6, which is 72. Okay, so here we have 72. And then for this one, a3 times v4, v3, 4. This is going to be equal to 6 times 4 times 5. 6 times 4 times 5. 4 times 5 is 20, times 6 is 120. So this is 120 operations. Now let's go to the more interesting case. So basically, I hope you already see this. We're going to fill in this table on the diagonal. So we're going to move up and up, right? So first we're going to fill in the diagonal, then 1 above the diagonal, then 2 above the diagonal, and so on. Okay, so this is basically how we complete this table. So v1 3. So we're interested in this entry here. So here in this case we can put the split at 2, at 1, or at 2, right? J can be equal to 1 or can be equal to 2. So if j is equal to 1, okay, let's compute first the cost there, and then we compute it for j equal to 2, and then we take the minimum of these two. Okay, for j equal to 1, well then, by the Bellman equation, we have that this is equal to v1, 1 plus v2, 3, plus the number of rows of matrix 1, which is 2, times the number of columns of matrix 1, which is 3, times the number of columns of matrix 3, which is 4. And now we already know these values. v1, 1 is equal to 0, v2, 3 is equal to 72, and this 2 times 3 times 4 is 6 times 4 is 24. Okay, so this is 96. Okay, of course j could also be equal to 2. In this case we have that this is equal to v1, 2 plus v3, 3 plus the number of rows of matrix 1 is 2 times the number of columns of matrix 2, which is 6, times the number of columns of matrix 3, which is 4. Okay, v1, 2 is 36, plus v3, 3 is 0, plus here 2 times 6 times 4 is 12 times 4 is 48, and this is going to be 70, 80, 84. And you see that you have to take the minimum of these two, right? 96 or 84. Now 84 is smaller, so we're going to put a1, a3 is going to be equal to 84. Okay, so this is basically how this computations go. Let's compute here a2, a4, v2, 4. Well, either we can put j equal to 2, and then you have v2, 2 plus v3, 4, and then the number of rows of matrix 2 is 3, number of columns of matrix 2 is 6, and the number of columns of matrix 4 is 5. Okay, and this is equal v2, 2 is 0, plus v3, 4 was 120. Okay, plus 6 times 5 is 30, times 3 is 90, so this is going to be 210. If j is equal to 3, okay, it's the second case that you have to consider, then you have v2, 3 plus v4, 4, plus the number of rows of matrix 2 is 3, times the number of columns of matrix 3 is 4, times the number of columns of matrix 4 is 5. V23, I look at my table, this is 72 plus 0 plus 4 times 5 is 20 times 3 is 60, so this is going to be 132. So I have to compare 210 and 132, so 132 is smaller, so this is what I'm plugging in here. Okay, and now we're at the final one. So let me take a new sheet of paper. I have to compute V14, which is basically the product that I want. That's the number I'm interested in. And here J can be 3 values, right? So the longer the distance between the matrices, the more values J can take, right? It's the more options where you can put a split. So here J can be equal to 1, can be equal to 2, or can be equal to 3. So if J is equal to 1, then I have V11 plus V24 plus the number of rows in matrix 1, which is 2, number of columns in matrix 1, which is 3, and number of columns in matrix 4, which is 5. So this is 0 plus 24 is 132 plus 2 times 5 is 10 times 3 is 30 is 162, right? Operations. If J is equal to 2, okay, then we have V12 plus V34 plus the number of rows in matrix 1, which is 2, times the number of columns in matrix 2, which is 6, times 5, the number of columns in matrix 4. So V12 was 36, plus V34 was 120, plus 2 times 5 is 10, times 6 is 60. Right, so here we have 180 plus 216, if I didn't make any mistake, right? Which is also a possibility, of course. And J equal to 3, then you have V13 plus V44. So we have V13, which is 84, V44 is 0, and then you have here to add, number of rows is of matrix 1 is 2, number of columns of matrix 3 is 4, and number of columns of matrix 4 is 5. So this is equal to 84 plus 0 plus 40, which is 124. So I have either 162 or 216 or 124. The smallest of these three is 124, so this is going to be the cost. Okay, so here at the end we put a split at 3, right? So we have V13 times 4 times A4. Okay, and in order to know what's the best split here, well, we can look at V13. V13, the best one was to put J at E2. Okay, so we had matrix A3, and then you had matrix A1 times A2, right? So this is basically how the result looks like. You first multiply matrix A1 and A2 together, then you multiply it by matrix 3, and then you multiply the result by matrix 4, and this gives you a total cost of 124. And you see, if you do it in a less efficient way, then the cost can be much, much bigger, right? So it makes sense before you multiply matrices together that you first compute the cost, and then once you have solved this Bellman equation, you know exactly what's the most efficient way to multiply these matrices together. So let's try to code up this example. Okay, so welcome to Julia. So here I already made a vector of the dimensions of the various matrices. Right? So here this is the dimension of matrix 1, dimension of matrix 2, and so on. Okay, so this is what I start with, and now I'm trying to write a function, matrix multiplication. This is going to take this vector of dimensions, and it's going to give me my result, and then I'm going to call mn to this vector. Okay, and at the moment it's not returning anything. So first of all, let me store in big N the number of matrices. So this is going to be the length of this vector. And I'm going to store the results in a dictionary that's called V. So it's going to take a tuple, which is going to be the integer of the starting matrix, the integer of the end matrix. So I'm going to compute the multiplication from this matrix until this matrix, and it's going to give me the number of operations that I need to do in order to multiply these two together. And then I also want to store the results. So for any tuple, starting matrix, finishing matrix, I'm going to store the results in, let me use a string. Right, so basically I would like to have something, sequence will give me something like 1 times 2 times 3, something like this, right? Which means that I first multiply 1 and 2 together, and then I multiply the result by 3. Okay, so this is what I would like to have. Okay, let's start with the base cases, right? So for I equal to 1 to n, if I multiply I by I, this is going to cost me nothing. And what do I need to do in order to multiply I by I? Well, I don't have to do anything. I'm just going to take I, convert it to a string, and put it into sequence. Okay. Let me return V in sequence. So far I don't have anything. Well, in order to multiply 1 by 1, I just take the matrix 1. 3 by 3, I just make the matrix 3, and so on. Okay. So now for my iteration. So remember, in filling in the table, I started from the diagonal, right? And then I considered entries further and further away from the diagonal. So let me call the distance from the diagonal, let me call this dist. Okay, so if I'm at the diagonal, I am at 0. So this already gives me, VII already gives me the values at the diagonal. So the minimum distance I'm going to consider is going to be equal to 1. And the maximum distance, right, is going to be equal to n minus 1. So from the first to the last matrix, this is distance n minus 1 from the diagonal. Okay. And then for a row, for I equal to 1 to n, this is going to be my row. So if I'm at distance dist from the diagonal, I don't have to consider every row, right? I only have to consider row 1 to n minus distance. Okay, so for example, if distance is equal to 1, I don't have to consider the last row because there's nothing. At the last row I have matrix 4, right? And I cannot put any matrix behind matrix 4 to multiply to it. Okay, so this is, I'm only going to have to consider row 1 to n minus distance. And then because I know the distance, I already know the last matrix, so J is going to be I plus distance. Okay, so basically I'm going to fill in at this table row I, column J, which is going to be the distance dist from the diagonal. Okay. And now I'm gonna have to loop for all k equal to I until j minus 1, right? So this is where I'm going to put the splits. I'm going to compute the value, right, which is going to be v ik plus v k plus 1 j plus the number of rows in I, which is dist I, the first element of this subvector, right? Dist 1, for example, is this here, but I only consider the row, so this is the first element, times the number of columns of matrix K, so this is dist K, the number of columns is 2, then the number of columns of matrix J, this is this J times 2. Okay, so this is basically, if I put a split at K, this is the total cost. And I would like to find the K that minimizes this. So what I'm going to do, I'm going to introduce a temporary variable that I'm going to initialize at infinity. If if putting the split at k is better, is improving the temporary value here, well then I'm going to update my solution, right? Then I'm going to put temp equal to this thing here. Okay, so I'm repeating this here. I'm going to put Vij number of operations equal to temp. I'm going to update this. And now for my sequence, so what I'm going to do is I'm going to open brackets. I'm going to multiply, so this is concatenation of characters, right? So it's multiplication. I'm going to the multiplication that I have from I to k, and I'm going to multiply this, right? This is multiplication sign. I'm going to put in my string, and I'm going to multiply this by k plus 1 until j. Okay, and then I'm going to close my brackets at the end. Alright, so this should look like this. I'm going to end this updating, and this one, and the eyes, and into distance, right? So we have several loops in each other, right? So this is looking at the distance from the diagonal, this is iterating over the possible rows, and then this is iterating over the possible splits, right? So if this split k improves my temporary solution, I'm going to update my temporary solution. I'm going to assign the cost to this temporary solution, and I'm going to update my sequence. So every time I find a better value, I'm going to run these three things here, so I'm going to update everything. Okay, so let's try to compile this. So I have a one end too many or one end too little. So this is the end here, this is the end here, this is the end here, this is the end here. So do I have one too much? Let me see. No. Right, so this compiles. I don't know what the problem was. So we have a bounds error. So what's the problem here? VII from this is one. Alright, let me pause for a moment and then come back to you to see what the problem was. Okay, so welcome back. So the mistake that I made is instead of having dims here, the dimensions, I put dist, right? So I was a bit confused because I called this dist, and then I use dist here. So these have to be the dimensions and not the distances here. And also here should be the dimensions and not the distances. Okay, so if I correct this mistake and compile again, then complete my solution, then what I see is that if I multiply matrix 1 up to 4 together, so 1, 4, this gives me total number of operations of 124. And how did I do this in the most efficient way? Well, first I multiply 1 and 2 together, then multiply this by 3, and then matrix 3, and then multiply the result by matrix 4. Okay, so this gives me basically the result. And of course I can add some more matrices, right? So for example, I can a 5 times 2 matrix, and then a 2 times 7 matrix. Okay, if I do this, I can easily run this again. And then for example, I think this is the 1 times 6. So first I multiply matrix 4 and 5 together, then with 3, then with 2, then with 1, and then finally with the 6th one. Okay, the 6th one is at the end because I'm going to exploit the fact that I only have 2 rows and 2 columns here, which will make the computation much more efficient. Okay, so thanks for watching. Welcome to this last video of Math-S401 dynamic optimization. So today we're going to look at the egg drop problem. So the problem is the following. You have let's say a basket of eggs, okay, and you have an apartment building, large building with a number of floors. Right, so this is 1, 2, 3, 4, 5, 6, and maybe the top floor, which is 7. Okay, the last one in the building. And the question is the following: at which floor does the egg, maybe I can reformulate it, question, what is the highest floor that does not break the eggs? Okay, so if I drop my egg from the first floor and it doesn't break, then I can consider the second floor. If it still doesn't break, I can consider the third floor. If it breaks from the third floor, then I know that the highest floor from which the egg doesn't break is the second floor. Okay, so that's the question. If the egg never breaks, then my answer is 7. If the egg already breaks from the first floor, then my answer is 0. Okay, and you assume that the egg never breaks at floor 0. Okay, so that's the question that I'm interested in finding out. And I can always do this, right? If I have an egg, what's the best thing to do? Well, it's to start from the first floor. If it breaks, then I know my answer is the first floor. If it doesn't break, I go to the second one, I drop it. If it breaks, then I know my answer is the first floor. If it doesn't break, it's at least 2, so I can go to the third floor and so on. Right? So by each time dropping the egg one floor higher, if it doesn't break, I can find out the answer to my question. Okay, so at most I can have 7 tries. Okay, so in general, if I have a building of n floors, then at most I have to try n times. Okay, so if I have one egg, that's indeed the optimal solution. I have to try consecutively every floor, and then this will answer my question. However, if I have more than one egg, I can be a bit more ambitious. Okay, so for example, assume that I have a building of 3 floors, 1, 2, and 3. Right, so if I have one egg, well, I have to drop it from the first floor, then I have to try it from the second floor, and then I have to try it from the third floor. So at most 2, 3 drops, let me call it, at most 3 drops are necessary in order to answer this question. If I have 2 eggs, I can be somewhat more ambitious. So for example, first I can try floor number 2. Okay, and if I try floor number 2, then either my egg breaks or it doesn't break. Okay, if it doesn't break, well, then I know that my answer is at least 2, so I can still have 2 or 3. So drop remaining egg from floor number 3, and then again my remaining egg can break or it doesn't break. Okay, so here the advantage is because I have 2 eggs. Well, no, let me come to this in a second. So here it doesn't break, I drop it from floor number 3. If it doesn't break, then my answer is 3, my answer to this question here. If it breaks, well, then my answer is 2, because it didn't break from 2, but it breaks from 3. Okay, now if at 2 my egg breaks, well, I'm lucky because I have still 1 egg left, right? So I can continue. Otherwise I had to stop and I would never have discovered the true answer. But here, because I have 1 egg left, I can drop it from floor 1, and then again it can break, and my answer will be that the highest floor from which the egg doesn't break is the 0th floor, and if it doesn't break, well, then I know my answer is 1 because it didn't break from floor 1 and it breaks from floor 2. Okay, so how many trials do I need here? Well, I first drop it here, so that's 1 trial, and then I drop it again here or here, right? So that's the second trial. So here, if I had 2x, I have at most 2 drops, and at most 2 drops I will be able to answer this question. Okay, so the question is now more general. Given that I have, let's say, EX and F floors, I can look at this question, which is derived from this question. What is the maximum number of drops necessary to answer question number 1? Okay, if this is question number 2, then I have this question. Okay, and this is basically the question that I'm going to solve. What's the maximum number of drops that I need with EX and F floors in order to answer, to determine the critical floor, right? The critical floor at which the egg still doesn't break. And you have seen, if you have 1 egg and 3 floors, you have 3 drops. If you have 2 eggs and 3 floors, then you have 2 drops, right? So the number of eggs actually gives you some more possibilities to be more ambitious, okay, to be more risky, because if an egg breaks, you still have 1 left. Okay, so we're going to write this as a Bellman equation, as you always do, right? So we have a value function that depends on the number of eggs, let's say, and the number of floors that we have in our building. Okay, and we're going to try to write this as a recursive equation with maybe a fewer number of eggs and a fewer number of floors. Okay, that's the idea here. So what will I do normally with my egg? Okay, I will drop it from some floor. Okay, so drop from J. So what happens if I drop my egg from the Jth floor? Well, then I have dropped an egg, right? So V has to increase by 1, right? That's a given. And then there are 2 possibilities, right? Either it breaks. Okay, so if it breaks, then I know that the critical floor is below J. Okay, so now I only have to consider, right? So if this is my apartment building, I have a number of floors. Okay, so if this is floor number J, which is right here, so if I drop my egg here and it breaks, then basically I only need to consider the smaller apartment building that starts from floor J minus 1. Okay, that's, and I already know how many trials I need to do there, right? Basically I need to do E minus 1 because my egg broke, right? I have 1 egg left, 1 egg fewer left, and now I have a building of J minus 1 floors, the smaller one. Okay, if it does not break, well, then basically I have all my eggs left, right? Nothing broke. And I know that the critical floor is either J or above. Okay, so basically what I can do is I can consider this sub building, which now has F minus J floors, right? F was the top one here. So this is like an apartment building with F minus J floors, and I have EX left to determine which one is a critical floor here. Okay. I don't know which one breaks, which one of these 2 cases will be the actual case. So depending on whether it breaks or not, I either have to try so many times or I have to try so many times, right? And I'm risk averse in the sense that I really want to know the critical floor, so I have to take the maximum of these 2 things. E minus 1, J minus 1, and VE F minus J. Okay, And then of course I have 1 plus this thing here. So this is more or less my Bellman equation, except that here I chose the floor j from which I drop the egg. I want to know the minimum number of trials that I need to do. So I'm going to choose the floor j that minimizes this expression. Okay, and j is going to be between 1 and f. Okay, that's basically my Bellman equation. V e of f is going to be the minimum over all j's between floor 1 and floor f of 1. That's the egg that I drop at the jth floor. And then depending on whether the egg breaks or doesn't break, I'm going to have to try so many times in addition or so many times in addition. Okay. I also have some base cases. So basically you can already see if I only have one egg and f floors, I'm going to have to be conservative, right? If I drop from some high floor and my egg breaks, I have nothing left and I cannot determine the critical floor, right? So if I have one egg, I have to first start from the first floor, then go to the second floor if it doesn't break, and so on and so on. Okay, so at most I will need f trials to determine the critical floor. That's my base case. And of course, if I have some eggs and I don't have any floor, then I don't have to do anything, right? So maybe that's another base case. Okay, so let's try to put this in a table, and I'm going to consider an easy example. So I have 6 floors, 1, 2, 3, 4, 5, 6, and I will only consider the case with 2 eggs. Okay, I already know from the base case, if I only have one egg, then this will just be copy pasting. Now I have 2 eggs and 0 floors. I have 0, so I just wish to compute all of these points. Okay, so let me start by computing v2 of 1. So in this case I have 1 floor, so j can only be 1. Okay, here I minimize with respect j between 1 and 1, so j has to be equal to 1. So I have 1 plus the maximum of v. If it breaks, I have 1 egg left and 0 floors, and if it doesn't break, I have v2 of 1 minus 1, which is 0. This is 0, this is 0, so this will be equal to 1. Okay, so this is a very easy case. There's only one j to pick. The value is going to be equal to 1, so this is going to be equal to 1. Okay, v22, 2x, 2 floors. Well, I can drop my egg from floor number 1, or I can drop it from floor number 2. Okay, so let's see what's happened here. Here I have 1 plus the maximum of v. If it breaks, I have 1 egg left, and drop it from floor number 1, so 0 floors left. If it doesn't break, I have 2 eggs left, and 2 minus 1, this is 1 floors left. Okay, v10, 1, 0 is 0, 2, 1 is 1, maximum of 0 and 1 is 1, 1 plus 1 is 2. Here I have 1 drop plus the maximum of v. If it breaks, I have 1 egg left and 1 floor. If it doesn't break, I have 2 eggs left and 0 floors. v21 is 0, v11 is 1, the maximum is going to be 1, 1 plus 1 is going to be equal to 2. So independent of which floor I'm taking here, I think you can already see this, the number of drops is going to be equal to 2, so this is going to be 2. Okay, let me take a new piece of paper, and now I'm gonna want to look at v23. So in this case I have 3 options: drop it from floor number 1, drop it from floor number 2, or drop my egg from floor number 3. Every time I have 1 plus. So here I have 1 plus the maximum of v. My egg breaks, 1 egg left. but I don't have any floor left here, or v 2x left. Okay, v 2x left, 3 minus 1 is 2. 1, 0 is 0, 2, 2 is 2, the maximum of 0 and 2 is 2, plus 1, so this is 3. Here I have the maximum of 1 egg left and 1 floor left, and v 2 eggs left and 3 minus 2, which is 1, right? v11 is 1, v21 is 1, maximum of 1 and 1 is 1, 1 plus 1 is 2. Okay, so this is smaller than the tree here. Dropping it from the second floor is the optimum thing to do. And here I have the maximum of 1 egg left and 2 floors, and 2 eggs left and 0 floors. 2, 0 is 0, 1, 2 is 2, maximum is 2, plus 1 is 3. So here the best thing will be to drop it from the second floor. Alright, this gives me 2 drops in total. v2, 4. So now I have to expand, right? J can be equal to 1, j can be equal to 2, j can be equal to 3, and j can be equal to 4. So I have 4 possibilities here. So I have 1 plus 1 plus 1 plus 1 plus, here the maximum of v10 and v2 3. Okay, 1, 0 is 0, 2, 3 is 2, maximum is 2, plus 1 is going to be equal to 3. Here I have the maximum of v11 and v2, 4 minus 2 is 2, 1, 1 is 1, 2, 2 is 2, maximum is 2, plus 1 is 3. Here I have the maximum of v12 and v2, 4 minus 3 is 1, 1, 2 is 2, 2, 1 is 1, maximum is 2, plus 1 is 3. And here I have the maximum of v1 3 and v2, 4 minus 4 is 0. 2, 0 is 0, 1, 3 is 3, maximum is 3, plus 1 is 4. So here every action is optimal except for the last one. Okay, you don't want to drop it from the 4th floor. Because it breaks, then you have to go over all other 3 of them, which will take you 4 trials. Okay, so here all of these are optimal. And you have a total number of drops equal to 3. Okay, v2, 5. Now I have 5 options. Let me put my table here. Okay, so j equal to 1, j equal to 2, j equal to 3, j equal to 4, j equal to 5. Okay, I have 1, 1, 1, 1, 1, plus, 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 plus. Here I have the maximum of v10 and v24. 1, 0 is 0, 2, 4 is 3, so here we have total number of 4. Here we have a maximum of v1, 1, and v2, 5 minus 2 is 3. 1, 1 is 1, 2, 3 is 2, maximum is 2, plus 1 is 3. You have the maximum of v12 and v22. 1, 2 is 2, 2, 2 is 2, maximum is 2, plus 1 is 3. You have the maximum of v 1 3 and v 2 1. 1 3 is 3, 2 1 is 1, 3 plus 1 is 4, so this is not going to be optimal. And you have the maximum of v 1 4 and v 2 0. 1 4 is 4, 2 0 is 0, 4 plus 1 is 5. Okay, so here either floor number 2 or floor number 3 is going to be the optimal. Okay, so this was 5 floors, and then finally, so here I have to put 3, right? And then finally we have v2 6. I have 6 possible options: floor number 1, floor number 2, floor number 3, floor number 4, floor number 5, and floor number 6. Okay, so 1 plus the maximum v1 0 and v2 5. 1 0 is 0, 2 5 is 3, plus 1 is 4. 1 plus the maximum of v1 1 and v2 4. 1 1 is 1, 2 4 is 3, plus 1 is 4. Here I have 1 plus the maximum of v1 2 and v2 6 minus 3 is 3. 1 2 is 2, 2 3 is 2, maximum is 2, plus 1 is 3. And here this is 1 plus the maximum of v1 3 and v2 2. 1 3 is 3, 2 2 is 2, biggest is 3, plus 1 is 4. 1 plus maximum of v 1 4 and v2 1. 1 4 is 4, 2 1 is 1, 4 plus 1 is 5. 1 plus the maximum of v1 5 and v2 0. So this is 5, 5 plus 1 is going to be 6. Okay, so here we see that the optimum is floor number 3, which is going to give you 3 drops. Okay, and working backwards, you can actually every time you go further, you can re-optimize and you can see the optimal number of floors, right? And particular, you can also add more eggs, you can add more floors and so on, and see what the optimal number of drops is. Okay, so this is basically how the problem is solved. Maybe also have a look at how this works. So for every floor, for every problem, so basically how many problems do you have, number of floors times the number of eggs, right? And for every one of these floors, you basically have to compute f subproblems, right? And then take the minimum of those two, right? This is one subproblem, this is another subproblem. Okay, so basically e times for every f, for f equal to 1 to n, you have to compute f subproblems. So this is something like the total number of computations that you need to make. Okay, and you can work this out. So in particular, this is going to be e, and then it's going to be 1 plus f times f divided by 2, something like this. Okay, so this is going to be of the order e times f squared, right? Because you have a square here, right? So the number of floors actually is going to be a square here when you look at the computational complexity. Okay, so let's see how this works when you try to program it. Right, so I have a number of floors, a number of eggs, sorry, and a number of floors. Alright, so let's try to write a function egg drop, okay, given some eggs and given some floors. Okay, I'm going to introduce a value function. Again, I'm going to take a dictionary. It's going to take a tuple, depending on the number of eggs I'm going to give it and the number of floors I'm going to give it, and it's going to reduce me the number of drops that I need to make at most in order to determine the critical floor. Okay, I'm going to return v and so on. So there are some base cases. So in particular, if the floor is equal to the 0 floor, v e of 0, this is going to be 0, no drops are needed. And for f equal to 1 to floors, if I only have one egg and f floors, then it's going to take me at most f trials to determine the critical floor. Okay, so far, if I run egg drop for 2 eggs and what was it, 6 floors, I'm just gonna have my base cases. Okay, 1 egg, 2 floors, 2 drops. Okay. Now comes the fun part, right? So what I'm doing, I'm going to go row by row, right? So for e equal to 1, 2, right? Because I already have the 1 egg case here. 2 eggs. For f 1 2 floors. Well, I'm gonna see if I drop it from floor j. Well, then I have 1 trial plus the maximum of 2 things. Remember, v e minus 1. If my egg breaks, I have e minus 1 eggs left and a building with j minus 1 floors. If my egg doesn't break, I have e eggs left and f minus j floors. Okay, so basically what I'm doing, I'm looking for the j that minimizes this thing here. So I'm going to introduce a temporary variable that's going to start with value infinity, and then for j equal to 1 to f, if temp is bigger than this, then I'm going to update my temporary variable to this thing here, and I'm going to set VEF to be equal to this thing. Well, I can put it equal to temp. Okay, so I think this should do it. Looks good. So if I run it, let me store it in the dictionary v. So v add x, add floors. I have 3 trials, right, which was exactly what I got. So it gives me the same answer, only a little bit faster, right? The computer can compute faster than I can. So for example, if I would have 4 eggs and let's be ambitious, 300 floors. This is a huge building. Right, I can run it, it runs. I need 10 trials at least to determine the number of critical floors. Although I have 300 floors, right, which is quite high. So this number doesn't grow that fast in the number of floors. Okay, so thank you for watching.